Okay, so last time we introduced the notion of an affine connection, and we saw that an affine connection was specified in coordinates by its Christoffel symbols. And so there's kind of a correspondence between these functions, the Christoffel symbols, and affine connections, provided that the appropriate transformation rule is satisfied. That I didn't tell you what it was, okay? Today what we're going to see is the kinds of things that you can do with affine connections. Okay? And there's a bunch of things you can do with affine connections. We've kind of already talked about one, which is that you can use affine connections to differentiate vector fields with respect to other vector fields. Okay, and that idea by itself already leads to other useful constructions. Okay, so let's start to talk about that kind of stuff. Okay. Okay. All right. Let's we've differentiated a vector field with respect to a vector field. Let's see if we can do other kinds of operations with affine connections. And so the first one is this. So let y be a vector field, smooth, let's say. And let Vx be a tangent vector at x. Okay. And so what I'm going to do is I'm going to just define the derivative of y, not with respect to a vector field, but with respect to the single tangent vector. So there's kind of an obvious way to do that. And that is, you say let x be a vector field such that x at x is equal to v sub x. Okay, so then we can define nabla v sub x y, okay, to be nabla x y, all of this evaluated at x. Okay. All right. So you have to check that this definition makes sense. Okay, because in making this definition, what I've done is I've taken the single tangent vector v sub x and I've extended it to a bunch of tangent vectors at every point in M by virtue of the vector field x, and I've done so in such a way that this condition is satisfied. Okay, the question is, does that definition depend on capital X? And well, it pretty clearly doesn't, and let me explain to you why. So this definition is independent of x. Okay, but up to, of course, the fact that x has to satisfy the condition that I asked that it satisfy. Okay, so if you choose any other x that satisfies this condition, the point is the definition will still, or the same quantity applies. And the reason why, and maybe this, the simplest reason is to just remember what the coordinate formula for the covariant derivative is. So I'll write that down. And then emphasize the thing that I care about. Okay, so that's the coordinate formula for the affine connection that we derived last time. And there are its Christoffel symbols. Okay, and the point here is that x here appears linearly. Okay, so the only appearance of x in that formula is through its values at a given point. And so in particular, if you evaluate this thing at x, then you can put Vx here and you can put Vx here. Okay, and so it's the linear dependence on x that gets us the independence that we're after. Okay, so for example, just to clarify what kind of a construction could go wrong. So for example, so maybe for comparison, consider the Lie bracket. Okay, and so we could just do the same kind of a construction as we did here. We could say, take a tangent vector at x, choose a vector field that extends it like so, and then define the bracket of Vx with y by this formula. Okay, so let's try to do this. Okay, we could wrongly, as we'll see, okay, so the adaptation of the previous construction would look like that, right? And so you again choose a vector field x that satisfies the condition that's value at x is equal to the tangent vector that you like, and you say, there's my definition of the Lie bracket of a tangent vector with respect to the vector field. Okay, and this definition is not well posed. Okay, and the reason is exactly the same reason why this one is, and that is that if you write down the coordinate formula for the Lie bracket, you'll see exactly why it doesn't make sense. And so I'll repeat that here. Okay, and it's that term that gets you, right? So if you were to change, if you were to specify two vector fields x, okay, that satisfy this condition, it's entirely possible, in fact, quite likely, that their first derivatives at x will not be the same. Okay, just because they satisfy this condition at x does not mean that their derivatives at x will be the same. So it's, okay, this prevents the validity of the definition. Okay. All right, so that's one thing you can do. And now we're going to extend that slowly in different directions, okay? The first thing we're going to do is just a direct, it follows directly from what I just did. So now given a curve gamma on M, okay, and a vector field y, just as above. Okay, I will define this thing, which I'm going to write like so. So this is going to be nabla gamma prime y. Okay, and so gamma prime consists of the tangent vector field along the curve gamma, and so you can just imagine what we're going to do is at every time t, we're going to apply the construction that we just gave. Okay, and then what kind of an object do you get back? Well, what you get back is you get a vector field. Okay, so at every time t, okay, this thing gives you a tangent vector, and of course, it's going to give you a tangent vector at time t. It's going to give you a tangent vector at gamma of t. Okay, we can define this thing, which is a vector field along gamma. Okay, so this is what I mean by that is I mean that nabla gamma prime y at t is in the tangent space at gamma of t. Okay, so there's a picture in your mind that should go along with this. Okay, and it goes something like this. Okay, so here's my curve gamma, like this. All right. Now I also have a vector field. Okay, so the vector field y. All right, so let me draw y in, and it does whatever it does. Okay, and in particular, at points along the curve gamma, there's a tangent vector like so. Okay, and so if this point right here is gamma of t, okay, that tangent vector will be y at gamma of t. Okay. All right. And then what I'm doing is, okay, then I have the nabla gamma prime y of t is equal to, well, again, it's like I said, it's the obvious definition using what I've already defined. It's nabla gamma prime of t y, okay? Because this, after all, is just a tangent vector to m at gamma of t. Okay, does that make sense? Okay, and so at this point, I will get some other tangent vector. Okay, and now my drawing is getting a little cluttered, so forgive me, I'm gonna rub some crap out. Okay, I'm gonna get some other tangent vector, and it's gonna look maybe like this. Okay, and okay, and that one's gonna be nabla gamma prime y at t. Can you see it first of all? Probably you can see it easier than I can because it's blown up on the screen. Okay, and so the idea is that along this curve gamma, I have two collections of tangent vectors at every point. One are the tangent vectors given to me by y, Okay, and then I'm defining, essentially the way you should think about this is I'm differentiating y with respect to gamma. Okay, so I'm differentiating y along the curve. Okay, and then when I do that, I get some other tangent vector like this. And so this is maybe a good opportunity for me to try my colors. Okay, so this is this thing. Okay, and then this is y composed with gamma t. Okay. Oops. There. Okay, does that make sense? Or at least, you know, we need to write down what this thing actually looks like to calculate it, but conceptually, that's what it is. Okay. So in coordinates, x1 up to xn with the local representative of gamma being t goes to x1 of t, xn of t, like so. Okay. The local representative of nabla gamma prime y is, okay, and so I'll be right back, sorry. Okay, so it's this formula that I have up here, and then the only difference is that x is replaced with gamma prime. Okay, and so it's nabla gamma prime y of t. Okay, so all right, so like I said, it's the same formula. So it's dy j by, let me write it as, yeah, no, j is fine, whatever. D x k. All right, let me, I don't always do this, but because it's kind of conceptually important here, let me indicate where that derivative is evaluated. It's evaluated at the point, just like in the picture. Okay, it's evaluated at the point gamma of t. And yeah, so gamma of t. Okay, then it's x, sorry, but x is being replaced by gamma prime here. And gamma prime in coordinates is x dot. Okay, so that's x, oops, x dot k of t, okay, plus gamma j k l. Okay, then it's xk, capital xk, but capital xk is x, little x dot. Okay, and then y l and y l is evaluated at gamma t. Oh, sorry, j. Okay, and so the way normally you don't write this in such a messy way. You don't include all the arguments, and you just write that this is d yj by d xk x dot k plus gamma j k l x dot k y l d by d x j. Okay, and the arguments kind of just are what they have to be, but in the line above I prescribe them just so it's clear. Okay. All right, now when you write this formula down, you notice something here. Does that term look like it might simplify, or not necessarily simplify, but become something different? And maybe let me to try to make it the answer to my question more obvious. Does that look like it should be, it's trying to be something else? Chain rule? If you apply the chain rule, what does this thing look like? Right, so I'm going dyj by dxk, dxk by dt. That's right. So it's this whole thing is really just dyj by dt, right? Because if you were to take dyj by dt and just expand it using a chain rule, that's what you get. Okay, so now we observe that if we have not a vector field y defined everywhere, okay, but a vector field y only defined along the curve, okay, because that expression, dyj by dt, that only depends on the values of the vector field along the curve. So what we're going to do is we're going to replace the vector field, which is defined everywhere, we're going to replace that with a vector field that's only defined along the curve. Okay, so if we have a vector field y along gamma, okay, and again, all this means is that, is that y of t is in the tangent space at gamma of t, okay? Because in my picture up here, which I'll try to keep, okay? In my picture up here, although the y's were defined at points away from the curve, I don't actually really care about anything except the y's that are along the curve, okay? So that's why the construction that I'm going to do now makes sense. Okay, so if we have a vector field y along gamma, we can define a vector field nabla gamma prime y along gamma by, okay, asking that y bar be a vector field defined everywhere now, satisfy that y bar at points along gamma equals y. Okay, so what I'm doing is I have a vector field y, which is only defined along the curve gamma. So it only gives me a tangent vector at every point along the curve gamma. What I'm going to do now is I'm going to extend that vector field off the curve, and I get something which I'm going to call y bar. Okay, and I'm going to ask that y bar at points along the curve agrees with y. Okay, now you can ask, does such an extension exist? Well, that's actually not so easy a question to answer. For all intents, the answer is, for all intents and purposes, yes. Okay, but let's just sort of cast aside those little technicalities for the moment. Okay, so now having done this, then I can define nabla gamma prime y of t equals nabla gamma prime y bar at t. Okay, so I'm just using the construction that I just made up here. Okay, to define this derivative just for vector fields along the curve. And so in coordinates, Okay, and so we already decided that this was dy by dt. Okay, so it's just exactly the same expression with this replaced by its chain rule equivalent, dy by dt. So, sorry, it's y j dot plus gamma j k l x dot k y l d by d x j. Okay. All right, good. So what we've done is successively define a bunch of constructions, all of them very similar to one another, but one building on the other. Okay, so we started by talking about the covariant derivative with respect to just a tangent vector. Then we talked about the covariant derivative along a curve by applying the construction at every point along the curve. And then finally, we applied the same construction, but where y was only a vector field along the curve, not a vector field that was defined everywhere. Okay, so by a sequence of constructions, we end up here. And now we're going to do one more thing. And that is I'm going to apply this construction to a very specific curve, a very specific vector field y along the curve, because every vector field, every curve comes equipped with a natural vector field along itself, namely gamma prime. Okay, so this construction applies in particular to y equals gamma prime. Okay, and so there's nothing to do now. It's just a special case of the previous formula. Okay, but the formula or the equation in coordinates now looks a little bit different, because now I know that yj is xk dot. Okay, and so therefore yj dot is going to be xj double dot. In coordinates, nabla gamma prime is x double dot j plus gamma j k l x dot k x dot l. Okay, now that looks rather, if you just replace the general gammas with the Levi-Civita gammas that we talked about last time, the coefficients here, those are exactly the Euler-Lagrange equations for the kinetic energy Lagrangian. Okay, but now we've derived this not for anything to do with mechanics. This has to do only with affine connections. Okay, and so what we see is a specific mechanical thing has a general geometric interpretation in terms of affine connections. And so the Euler-Lagrange equations for the kinetic energy Lagrangian are that this is equal to 0, right? Okay, so then the question is, what does it mean for that to be equal to 0? Okay, well, curves gamma, which satisfy that condition, are very important. So if gamma is a curve satisfying nabla gamma prime equals 0, okay, we say gamma is a geodesic. okay? And it's for nabla, right? You change the connection or the affine connection, and the geodesics will change because, of course, in that differential equation above that describes what nabla gamma prime is, when you set that equal to 0, that'll change when you change the gammas, of course. Okay, so this is a geodesic is a thing which applies to the affine connection, not just to the manifold. Okay. So in coordinates, a curve gamma is a geodesic. If and only if nabla gamma prime of t is equal to 0 for all t. Okay, which means in coordinates that x double dot j of t plus gamma j k l x dot k t x dot l t is equal to 0. Okay, and so this thing is now a second order ODE. Okay, so geodesics satisfy differential equations. Okay, so what does geodesics mean? So let me tell you some things about geodesics. First, let's look at an example, and then what I'll do is I'll say some general things of which that example is a specific instance afterwards. Okay, so let's look at a very simple example. Okay, so we're going to take m equals R2. We're going to take G to be the Euclidean metric. And in case it's not clear what that means, I'll tell you what that means, because that word Euclidean has many, many different places where it arises, and here is one that is specific. Okay, and nabla G is going to be the Levi-Civita connection. Okay, so what's the Euclidean metric? So we're working on a simple manifold here, right? We're working on a Euclidean space, all right? So obviously Euclidean makes sense there, all right? So what this means is this, is that for x in R2, okay, the tangent space at x, okay, so we've seen this multiple times now. Tangent spaces to open subsets of Euclidean space are can be identified with the Euclidean space. Okay, so every tangent space is are isomorphic to as a vector space R2. Okay, and we take G of x to be the Euclidean inner product on the tangent space. Okay, because the tangent spaces are just R2, and R2 has its normal Euclidean inner product. Okay, and so in coordinates, so in Cartesian coordinates, x, y, for R2, okay, G is equal to dx tensor dx plus dy tensor dy. Okay. Let's make sure that we understand why that's the right formula for G. Okay, if G is supposed to give you the Euclidean inner product on each tangent space. Okay, so to verify this, indeed, if U and V are tangent vectors at some point, let's say x, y, and again, that's just isomorphic to R2, okay, then we write U is Ux d by dx plus Uy d by dy, and we write V as Vx d by dx plus Vy d by dy. Okay, so that's just writing down what those tangent vectors look like in coordinates. So the components are Ux and Uy and Vx and Vy. All right. Now, if we then evaluate G of U and V, what do we get? Okay, so we're going to stick U and V into this expression for G. Okay, so I'm gonna blow this all up. It's simple, but you should do the calculations once in your life in full detail. Okay, so it's dx tensor dx plus dy tensor dy. Okay, so that's the bilinear mapping. Okay, so remember that this means, whoopsie. Okay, that this means this tensor notation means that this thing is bilinear map, and so is that. Okay, all right, and these are applied to two vectors, Ux d by dx plus Uy d by dy and Vx d by dx plus Vy d by dy. Okay. All right. So it has these two arguments. That's U and that's V. Okay. So this is just G acting on U and V. Okay. So now we just calculate that using the rules of how this notation for bilinear maps works. Okay, so first of all, everything is linear with respect to scalar multiplication and vector addition. All right, so that means I can distribute all of these sums. Okay, and there's all over one another. Okay, and so what I get is I get dx tensor dx applied to U. Okay, so that's Ux d by dx plus Uy d by dy. I'm sorry if I'm belaboring this, but I just want to make sure that we all understand how to do these fairly simple computations. Okay, plus dy tensor dy applied to the same thing. Okay, so I've just distributed this across that addition there. Okay, so now let's look at the definition of dx tensor dx. Okay, remember what this tensor symbol means. Okay, what it means is that when I give it two arguments, like I'm doing here, I give the first argument to dx, or to the first of these things, and then I give the second argument to the second. Okay, so let's think, because I'm getting tired of writing down this all the time. So let's think a minute before we write. Okay, so if I go dx acting on that, what am I going to get? Well, I'm going to get dx acting on this one plus dx acting on this one. What will dx be when I evaluate it on that? Say it again. Yeah, exactly, because dx dy, right, the basis for the cotangent space is dual to the d by dx d by dy basis, and so that means, when you act on dx by d with dx acts on d by dy, that's 0. Okay, good. And so then this one, similarly, the d by dx will be 1. And now the same construction applies to all 4 of the things that are happening here. And the point is, when the dust settles, I get ux vx plus uy vy. Okay, all right. And this is just the Euclidean inner product of u and v. Okay, so that whole big long computation, right? That's like the dot product, okay, of u and v. Okay, so the whole long computation was just to verify that this is indeed the Euclidean metric. Okay. All right, good. Now, what are the Christoffel symbols? Okay, well, I'm going to save myself a bunch of work here by thinking about it before I calculate. Okay, the components of G are 1 and 1 there, and then there's 2 other ones, the dx tensor dy and the dy tensor dx. Those ones are 0. So the point is that all the components of G are constant with respect to x and y. They're not functions of x and y. The Christoffel symbols, on the other hand, all involve the derivatives of the components, right? There's some formula that I'm not going to write down here because I just don't feel like it. But the formula for the Levi-Civita Christoffel symbols involves derivatives of the components of the metric. Since the components of the metric are constant, those derivatives will all be 0. So the Christoffel symbols are all 0. Okay. All right. So then the geodesic equations are simply, okay, so they're those equations, okay, written down with the specific Christoffel symbols, which are 0. And so really they're just going to be x double dot equals 0 and y double dot equals 0. Okay. Now I claim you know how to solve those equations. What are their solutions? Well, they're just, you can just integrate them, right? You don't even, there's not even a differential equation really to solve. You just integrate twice, and you get x of t is x0 plus v0t. Okay, so x0 and v0 are the initial position and velocity at time 0, and similarly, y of t is y0 plus. So let me do it this way: u0t and v0t. Okay. And these, of course, are the equations, the parameterized equations for a line in the plane. Okay. All right. So note, things can get very complicated if you don't use the right coordinates. And so if you change coordinates here to, let's say, polar coordinates, okay, so Henry's going to do this computation in the tutorial, but G turns out to be in polar coordinates. So polar coordinates are theta. Okay, so G in polar coordinates turns out to be this. Okay, and this answers a question that we had, that you had. I'm sorry, I forget your name, sitting in the front row. Yeah, sorry, you asked it. Remember you asked this question about the, we had that rotational vector field, and I said in polar coordinates, it was d by d theta, and you felt like that wasn't quite right because the lengths didn't work out correctly. Remember that? Yes, so this is where we see the explanation for that, okay? And the reason is because when you write down the thing G, which measures the length, right? Because G tells you what the length is because it gives you the inner product on the tangent spaces, the theta component is scaled by r squared. Right, so that r squared kind of cancels with your intuition, and the lengths work out so that the length of that vector, d by d theta, indeed goes to 0 as r goes to 0. Okay, yeah, so, okay. All right, so that's what the metric looks like. And like I said, Henry's going to work this out in the tutorial. Christoffel symbols are not too bad, but I would say they fall in the category of a bit ugly. In particular, they're not 0. Okay, and the geodesic equations are unrecognizable. And by that, I mean, if somebody just gave you those equations, for r double dot and theta double dot, you would never just look at those and say, well, obviously the solutions of those equations are straight lines in R2. Very much not clear. And in fact, only when you write it in the right coordinates does that kind of make sense, okay? So, the thing I want to point out, and the thing that we'll look at in more general setup tomorrow, is that if anybody's here tomorrow, will anybody be here tomorrow? Some people, okay. Is that what property do straight lines have in Euclidean space? They have lots of properties, of course. One property is that it minimizes the distance between any 2 points, right? And so in this case, the geodesics minimize distance. And it turns out that's true in general, but in order to make sense of that, we have to do some stuff. Okay, so tomorrow we'll talk about the fact that geodesics on Riemannian manifolds minimize distance. Okay.